I know, it's the worst part.
It's actually super tasty.
I know so much.
Put a little sriracha, whatever.
Okay, so we're good to go.
I go outside.
Maybe put some chicken in it. You really just upgraded your meals.
Oh yeah. Next level. That's pretty depressing.
Next level good stuff.
Okay, let's get started. So, second the lecture on quantum physics class today. So, before we get started, let's first get a recap what we talked about last lecture. So let me first give you a previously on PSC 710. Should we have some background music? Some recap, things like that. Let me do that. Okay. Let's do a previous recap. So, someone can help me, give me some hint what I talked about? I kind of forgot what I talked last class.
Free joint
And
free chain model, free rotation chain model, and the rotation angle.
Yeah, great. Great. That's all we talked about. But let me follow the timeline where we started. We started to talk about what is the physical size of quantum chain. Could it be in real life? We talked about how long if you have a fully extended polyethylene chain. Somewhere if you have about 3,000 polyethylene, right? You have about 3 micron size. And we started then talks about, if they're fully compact, it's about 5 nanometer. Then we start to jump down more specific about different chain models. And we talked about a very ideal case, which is free jointed chain in model 1, right? So in this case, all the joints between all the chains are very flexible. We get down into the last part of the class where we just touch the base a little bit about what's the physical dimension of this and how does it depend on the how many bonds around the chain, right? So we got into the conclusion that your end-to-end distance will be close to NL squared. Okay. We also talked about a little bit more realistic model, which is free rotation chain. So where you have in the case that now your bond can rotate, but it has a certain fixed angle between different bond angles, right? We haven't discussed what this will be, and that's the goal of this class, is to talk about what would be an end-to-end distance for free rotation chain. Alright, so in between, we covered a little bit about what is the concept of vector. What's the difference versus a vector versus a magnitude, or just let's call it a number. We gave the example of how, if you go to New Orleans, how you go to Houston, they're different because you now need to consider not only the number, but also the direction. Okay? And we also talked a very little bit about how different symbol means in the quantum physics class, where you would have, this is called absolute, which is basically convert a vector to a number. We call it the sum function, where basically tell you if you add everything together, that's a sum. And we have one last symbol, which is average, where you will talk about what's the average between everything in the particle. So today we're gonna dive a little bit deeper. So think about last class as you just started learning diving. Today we're gonna go really deep. We're gonna cover some of the mathematics, where some of you might have trouble, but I will try to slow down as possible as I can explain in more detail how we can get this free joint chain in a physics or mathematics perspective. I'll explain where we missed is like 100 steps, how we get this simple equation. Today we're going to talk about that, and we will come to this what's the number for end-to-end distance for free rotation chain. So that's a go for this class. All right, let's get started. I want to talk about how vectors works again in the chain model. So let's start with, again, free joint chain. FJC, not the KFC, FJC. So you got several individual carbon-carbon bond where you have L1, L2, L3, L4, L5. So imagine these are free rotation bond, and the distance between each of them is fixed as L. Okay, L is the bond length. Now we're going to look at end-to-end distance, this function. And we talked about what would be average for H. If you want just to get average of the vector, we discussed in the last class. For the vector, it's very simple. It's the beauty of vector is if you want to get the H, it is basically as simple as you just add all the vectors together. So you just add L1, L2, all the way to L5, right? That's the beauty of vector, so that we talk about vector but not number. And we haven't talked to about this function, but mathematics or mathematician invented this symbol so that they can be a little bit lazy about writing, because you don't want to write this all the time. Instead of write all this everything add together, you can just use a symbol. Now I'm going to explain a little bit clear. It's basically L with a small unit on the bottom, I, and you're just going to tell it L will start from number 1 and finish at number 5. Okay, this is basically the start. This is where sin is going to be n, and those are equivalent from top to bottom. Okay, we talked about what this value will be in the last class, right? Last year I talked about an example of how you can understand this as a drunk graduate student. I don't think that will be as fun as this year. We're going to talk about a drunk professor. So, think about the case like a drunk professor. He gets so drunk he doesn't even remember anything. So if he walked one step further or walked backwards, it's the same probability. And that's in real life could happen is a drunk professor, he didn't remember anything, or he just walked around and in the end he wakes up and he's more or less close where he started off. And the reason for that is since every direction is similar, so the probability of in the end what H will end up for free joint chain will be 0. We talked about it last time. Because think about this is L1. If you add the second component is L2, the probability for L2 to be this direction throughout this circle is similar. So if you average all the possibility, it will be 0. Okay? But this is not what would be useful for the polymer physics. Oh, hold on. What happened? Is it out of battery? I'm trying to reset about. Sorry about that. Come on. It's not happy. Let me see. Takes time to perfect it. Should be okay. All right, we are back. Perfect. So, as I mentioned, this this H directionality is not what we want. So, physics comes up another term called, we don't care where this is, but we want to know the average of this length. So this is something you want to learn for this class, is called end-to-end distance. A term talks about what would end-to-end would be for this particular polynomial, how far they would be away from each other. Okay? And we talked a little bit about this in the last lecture, where end-to-end distance basically will be so end-to-end distance, we can use REE. So these small two e's on bottom basically is abbreviation for end-to-end. REE will be root of, and I remember last class someone asked a question about why this would be the end-to-end distance. Because if you h multiply by itself, h squared is going to be equal to the absolute of h and take root of, it will be this. Okay, that's a reason we can do this transformation. All right, now, as I mentioned,
So you're basically bypassing all of the directions that would give you the zero sum.
Right.
Just getting rid of all the directions that we can get it meaningful and then.
right.
Okay.
Right. So we're gonna go a little bit deeper in the math so that I will explain to you how does these two terms come along. FJC and FRC, free rotation chain. All right. So we're gonna be it's gonna be a rough ride ahead. So buckle up, because I'm gonna start talking a little bit about math. And if you have anything confusing you, don't hesitate to slow me down and say, let's talk about this, okay? So, we're gonna first got a generic term, what is this RE would be, then we will talk a little bit more details about what they would be. Let's start with a simple example. Take this, just a 5 bond, okay? So I'll write it down as here, just a 5 bond system where RE would be equals to, now we know what is H equals to, right? H equals to L1 all the way up to L5. So let's plug this thing into our equation. And for the simplicity, I'm gonna rewrite this equation a little bit just to make everyone easier. So I'll write RE squared will equals to H squared. That makes sense, right? All right. Now I can basically write as L1 plus L2 all the way up to L5. That's one of the H. I'm going to multiply by it one more time. Does this make sense to everyone? Right? I just expanded this and use this equation right here. Now, this is a little bit math into this. How do you multiply the first versus the second part of the equation? Where will we ended up? How many terms we would have? Think about
25.
25. Perfect answer in the back. Because we got 5 terms here. This is another 5. If you multiply by everything here, all right, I'm gonna start writing. It's gonna be long, right? it will take up the whole this board, so I won't do that. Instead of write everything up, you basically understand the answer will be the first one multiplied by each individual of these, the second one multiplied individual over the second bracket, right? So you're basically going to get L1 vector multiplied by L1 plus L5, right? Then add L2, do the same thing. Everything adds up. You're going to do it all the way to L5 multiplied by L1, L5. Correct? So total would be 25 of them. If you add everything together, expand this equation. Does this clear to everyone? One question in the back?
You just factored up the equation.
Yes. So instead of write them into a long, lengthy equation, I'm going to do a little bit differently. I'm going to list them and arrange them into a table. So we always got to have L11, right? L1, vector multiply L1. And the second would be L1, L2, right? The third term would be L1, L3. So very simple one. So this is we can call it 1, 1, 1, 2, 1, 3. You will also get a 1, 4 and 1, 5. And you will see what's the reason I write this way. Now you have L1, L2, L1. Alright, I'm going to quickly write all of them out. Now I'm going to be 3, 1, 3, 2, 3, 3, 3, 4, 3, 5. I'm going to do it 2 more times. 4, 1, 4, 2, 4, 3, 4, 4. And last row will be 5, 1, 5, 2, 5, 3, 5, 4, 5, 5. Okay, so the reason I write all of them, because now there's some interesting math you can play and some interesting things. Again, this is 25 of everything we just see in this lengthy equation. And if you saw this large box, there's something that you can actually take them out and group them into 2 type of group of indices. The group 1 and group 2, they can be written differently. So anyone can make some suggestion where I would go, how would I group them differently? If you think about the dot, the mathematics about dot multiply, they would be different.
So like you could group your L4, L1 with your L1, L4.
Yes, because they were reversible. So this guy and this guy, they're the same. Similar for this one and this one, they're the same, right? Because the dot equation doesn't matter if you use 1 multiplied by 2 or 2 multiplied. They were interchangeable. Is there other thing we can group into this? Anything else?
Couldn't
consider multiplying a matrix with 5 rows by a matrix with 5 columns? And
Right, that's basically, it is, right, 5 row by 5 columns. Now we have 25 items in this box. We are trying to sort them into 2 categories. So let me give you a little bit hint. How about we take this row out? Is there anything special between this row? Diagonal, right? And it's multiplied itself. And if we cut this thing by diagonally, you will see this is the mirror for the bottom versus the top, right? Because they're the same. And now we can sort of, let's say, group into a group number 1, and this would be the group number 2 on this corner, right? And I can count the group 2 twice, and plus the group 1 will be everything in this matrix. And you will see why I'm doing this very sort of grouping thing, because there's some magic we can play for everything diagonally. What is it? So, we got 5 of diagonal items, right? Let's just call it L. I want to write out them first so that I can explain to you. L5 plus L5, so delta L5. And the reason for this group 1 is if you use dot pattern, they basically will be equals to L squared 5L squared. Everyone following why I can do this? It's perfectly fine. Well, let me explain why this one would equals to L squared. And now this is a number, this is vector. And did we talk about last class? What is the dot dependence? So this would be equal to L times 2, L1, right? And L1 again. Take an absolute of that, dot to the south, multiply by cosine theta. What does it say there? 0. Cosine theta 0 is 1. Oh, here's the trick, right? So this is basically 1. If you dot it itself, it will equal to L multiplied by L multiplied by 1 is L squared. Got it? That's the whole reason we are trying to group into 2 groups, because everything in this diagonal is gonna be very easy to convert to be L squared. So if we do this, we basically gonna be have 5 L squared, because we only have 5 diagonal items, right? And how about the rest? We still got 1, 2, 3, 4, 7, 10 items in here, right? We're gonna again rewrite them into another format that we can follow. Okay? So we took the easy part first. This diagonal one is most the easiest. We got it all sorted out. Then let's take a look at everything off diagonally. It's actually pretty simple as well. Yeah. So since we're doing this equation, I'm gonna play a trick. See if you can follow this. I can just write the rest of 10 items, right? There's left. It's total of 20 items because they're symmetric, so you effectively cut down to 10 items, right? of 10 turns in anywhere else there. What I'm gonna do is to write it very quickly, Li, Lj, and I would call I not equal to Lj. It's basically what it is, right? So if I is not equal to j, it's everything else in a diagonal term. So I would be coming from 1 to 5, and j would be coming from 1 to 5. That makes sense to you? It's just a very simple way to write the same equation. Because now you can start from I equals to 1, j equals not equal to I, so we're going to start with 2, and all the way go to 5. So using very simple equation, we just summarize this very lengthy long table. Hooray! Great! Fantastic! We now have a very simple way to write this equation. And it matters a lot because now I want to come back to this equation again. So our RE squared will just be equals to, in that particular case, will be 5 L squared, right? That's basically all the sins on the diagonally plus average Li, Lj, I not equal to j. Okay. So, beauty of mathematics. You just play the trick and everything gets so clear now. You only have 3 tiny items here. Can we do something even more advanced and simpler to get everything going? Sorry, I'm missing the vector here. This is not the vector because we already converted it, right? So how about Li dot Lj? What this means is Li is the I segment of the chain, Lj is the next one. If it's not equal to itself, the average of that for free joint to chain, as you would know, if it's free joint chain, so this can move around. So the average of this is 0, right? So for 3 joint chain, this term is 0. Because, as I explained, if you have average of all the direction, your L1 dot Lj will be cancel out each other because of the directionality. So effectively, the only term left is everything, or this term, which you can write Li dot Lj. They would be I equals to j, right? Anything equals to each other, they will be left into the first term. So now, coming from this very simple 5 bond system, let's do a little bit crazy since to expand to one generic polymer chain. We no longer have 5, but let's call it, we have total of n segments. Okay, not 5 but n. We're going to change here. If you look at this equation, this term will be the same, but now the first one, because you know have how many diagonal terms? Instead of 5, you're going to have n. That's basically how many bonds have. You would come down to this generic equation. There's a question in the left.
Yeah, so if Li and Lj were at right angles to each other using free joint FJC, would that equal 1, their dot product?
Can you repeat it again?
If Li, the vector of Li and
Mhm.
Lj were at right angles to each other, so
Right.
like orthogonal, their dot product would be 1,
It will be, no, 0 would be 0.
0 still?
Yeah,
Because it's cosine of 90.
right. Right, so in another way, what you can think about, as I explained in the last class, L1 dot Lj is equal to magnitude of I and magnitude of Lj multiplied by cosine theta. This theta is the angle in between, so last student asked the question about if theta equals to 90, this cosine theta is basically 0, right? So this will be 0. Okay, but since we are taking average in this equation, which means you need to consider all the possible angles. So the angle going this way will cancel out the angle going backwards way. Because the average, or let's put it this way. So this will be Li Lj cosine theta. If you take average of this, give it average. These are numbers, so they will not need to take average. So you can apply the average to the cosine theta. Since it's a free joint chain, all the cosine theta average about 360-degree angle will be 0. Okay, that's all the rationale behind all this. That's why free joint chain would give you this term to be 0. And how about the real physical word meaning? There's actually a meaning about dot term. So you can think about as the second, how long the second bond follows the first bond. So let me explain what I mean physically by saying that. So let's say first bond is going this direction. The second bond is going at angle. So if you look at this, if you combine these two, Lj cosine theta is Lj cosine theta, basically is how long this part is. So, or you can think about the projection of the second vector on the path of the first vector. And this part, Lj sine theta, is no longer needed to be considered. So the generic term, in the end, we talked about this, so we know this is going to be 0 for free joint chain. Right? So the conclusion will be for free joint chain, your end-to-end distance, so this will be equal to 0, right? So beautiful mass. This is what we, it has been removed here, but I promise you, that's what I wrote at the beginning of the class. Then we're going to play a little bit of math to understand how we get to free joint chain. End-to-end distance will equal to NL squared. Okay, so, or you can write it as IE. So, and think about the two length scale I talked about at the beginning of the lecture. You got a length scale about 3 micron is fully extended polyethylene, and 3 micron is fully extended, 5 nanometer is fully compact if you squeeze it. This right in between is what the polymer chain would be adopted in a theta solution. And I will discuss a little bit more in more detail what the theta solution is, but it's close to what your chain will adopt in the solution state. Okay? So you can calculate how this will be. It's somewhere between 30 and 40 nanometer if you do the math. Okay? So that's more realistic for a polymer. Not fully compact, not fully extended. Alright, we're going to take a break here before I start to discuss the next model, which is free rotation model. And we will take a 5 minutes break. And now, if you have a question about the first part of the lecture, Just let me know. Otherwise, we will resume in 5 minutes break.
Now your lecture makes more sense.
See?
It's an Osmo, right?
Yeah.
Oh, nice.
So it should be working.
Yeah. That was really nice.
Yeah. I got this. It just arrived yesterday.
Oh, nice.
Yeah.
Yeah, I was considering getting one. I mean, it seems really nice for.
You
like-
want to play with it? You can do it after class.
No, I'm good. Thanks, though.
Are you good?
Mm-hmm.
What was the, so you, we showed that vector Li,
Mhm.
dot product of Lj
Mm-hmm.
is equal to 0 for free joint chain model.
Right.
How does that let us get rid of the second term exactly?
How do we get there?
So that, because with that equal to 0, that is what eliminates the second term, right?
Right, exactly. So this term is basically gone.
Alright,
And for the next model, what we talked about, the second term will not gone if you have a fixed angle.
is not gone if you have
Yes, yes. If you have a free rotation chain or free joint chain, then we're going to discuss it in the second part of lecture. Because then, as you see, theta is not, average theta is not going to be 0.
Okay.
It will be a value. And it turns out to be, there's a little bit of math there, but it's not complicated.
Hello.
Where would that be at?
Okay.
Candy nose.
Hannah?
Candy nose. Yeah, that's a little brought it to my attention.
So as long as the two vectors.
Certainly on Saturdays.
On Saturday?
Football game.
Oh, yeah. I'm gonna go to that tailgate that Hannah's doing. Sounds like fun.
Hopefully they win again.
What's that?
Hopefully they win again.
Did they win last week?
Yeah, like 55 to like, by like an order of magnitude.
That's crazy.
Yeah.
By how many furlongs?
I don't know. How
Furlongs
many,
furlongs per fortnight? What is that, 100,000 is 30 miles per hour? That's the one thing that I retained from last class.
I lived in Perkins.
Yeah.
That's gonna help you over there.
Oh, it will.
How many
Definitely
Perkins
will.
do you squat?
Perkins. Isn't that like a type of beer? Like a
I don't know.
Or like a quantity? I just drank a Perk.
How heavy is a Perkin?
So the one I had for like 8 years was Storm, finals week of my senior year of college, and this is the only one I have. It's really well, so. Well, the 20.
Was it also
How's it
him?
going?
No.
Supposed to be nine gallons.
9 gallons.
So I tried to. One of the crazy.
I got that sugar for butter and cheese.
I had this little bag. Just with it.
Oh dear.
And I don't like it because I'm on a stick.
Yeah, it's hard to like clean it.
And I like getting it from that doesn't make sense, but okay.
Yeah, it's getting eggs.
Yeah, because you can't make a bag, so you can't, but.
Really
Or
hard.
say
Actually, I think I have a pink one at home or something like that.
Karma.
We had one girl in our class, their high school made them buy Caitlin's calculator. It was straight up like a computer and a calculator.
Surface Pro.
Oh, his computer.
Surface Book.
Or squirrel.
That's Becca. You just like,
How much RAM does that have? You know?
it's like before you talk about something and she just goes like, pull something straight out of left field.
I don't remember how much. About 3 years ago, so I don't remember. But
I want one of the,
Right. This one is
I want one of the
sort of
laptops that
light.
is,
I don't need to do anything, I just click.
Puster
start
and some
finish.
of
Oh.
That's pretty cool.
Is it still ongoing? My battery is good?
No.
All right, let's-
Asus, whatever, they're Asus. Asus. Yeah.
What was it called?
I have a really old one, it's like 25.
I googled it the other day and it was like $1,500.
Yeah.
I was like, oh, I can't afford that. It's a beautiful laptop though. It's like this big and it's
It runs so quickly.
yeah. We used to do this like use this program called Pro 2, and it was like supposed to be the exact same on everybody's computer, like
I could run like 2,000 iterations in like 5 seconds.
Yeah.
and
What
mine
classes
runs
do
like
you
an hour
help
and a half.
sessions for?
yeah. Like we'd run it and theirs would be done in a second, and mine would take 40 minutes to run. And I was like, wow, I want you
Can we switch them
I'm
to
pretty
like
sure
Friday
NASA bought PC, so we'll just use.
I think it is in
That's where he's working now.
For now?
He got a job as a
prior.
All right, let's resume the second half. We're gonna continue to talk about change statistics. The first part was like just the appetizer where it shows you a little bit of how these change statistics would be. The second part is gonna be the main course. It's gonna be a little bit heavy, but I hope everyone can stay with that, because if you finish that, we can go to Wizard, it will be easy. All right, so the second part gonna be a little bit more tougher one, because in the first part it's so simple, the mathematics worked out so well that in the end, all you need to remember end-to-end will just be proportional to individual bond lengths as well as root of n, or how many you polymerize it. It's not scaled linearly, because that is called contour length. Contour length would be just n l, right? Because you just add everything together, pull it straight, that would be the contour length. And end-to-end distance is somewhere just in between. There's another term we will talk later, it's called radius of gyration. And I won't spoil it now, but it's somewhere very close to this term. And it's a factor of 6. So how about a little bit more complicated model? Free rotation model. Your appetizer is finished. Your main entry is here. FRC. Let's get complicated, because still you can write the equation. The first part one differs for 2, right? You're still gonna have this term, Li dot Lj. This is generic, it doesn't depend on the model. So I just copied this equation. This does not depend on whatever model you take. It's just a rewrite of the first equation we have. I'm missing a square here. Okay. Perfect. So now this is still going to be totally the same, but this part is no longer as simple as 0. 0 is such a beautiful thing that you don't need to worry about anymore. So let's take a closer look how they would look like. Li dot Lj. And we have written as Li magnitude, right? Lj magnitude and cosine theta in between. And what's the definition of free rotation chain? Anyone can help me?
Where the bond angle is fixed, but the
Right.
bond is rearranged around that axis.
Right. So this theta is now not equal to 0, and it's fixed in one direction. So I can give you an example. If I hold my arm straight, now tilt with the angle, that's the bond angle in between. And this is fixed, so I'm no longer able to do this way, but I can rotate it around the axis. That's more realistic to the chemical bond. Think about a methane, so which the bond angle is fixed. while you can sort of rotate it around this sp2 bond, okay? So you can do this way, rotate this way. Well, it's clearly created a problem that you no longer can say average of cosine theta would be 0. Not true anymore. So how can we deal with this problem? All right, so the second half of the class is just to help you go through a little bit more complicated mathematics showed on the textbook. It is in the chapter 6.2. I'm gonna go through the math ones with you, but you're not required to memorize the process you get in there. The conclusion you should know, okay? So, it's not 0, it's basically a constant value, right? Constant number for free rotation chain. Because theta is fixed. Cosine theta is always going to be equal to some value. Alright, so you can sort of understand in a real world term. Let me show you again. I like to draw this. So now this theta is fixed. So you always have part of the last chain going projected down there. If you keep drawing the next one, this angle is again the theta. It will have same projection along this line, and if you project it one more time, you're going to have a little bit turn left, project down the first step. Then if you keep going, you still have a correlation between different chains, right? Even this is I, number I of the bond, this is number J somewhere. It might still have a little bit of fraction going to follow the first direction, although it's diminishing but still following. So how are we going to handle this problem? I have a crisis. I need dial 911. Someone help me, please. Please. Anyone? Anyone? All right. No worry. We will start take it slowly and approach the problem altogether. The first thing I like to do is I don't like to write cosine theta all the time, since it's constant as defined alpha. Alpha would be a constant, okay? So alpha is equal to cosine theta. So I don't need to write cosine theta all the time, I can just write alpha. So now, this basically equals to L squared alpha. If I equal I next to J, right? So in other words, if you have anything sitting next to each other, why it's important for I next to J? Because if ij are next to each other, we're going to project it just once. So L sine theta would be how much component left following the first direction. What if you have I minus j equals 2, or there are 2 bonded away? So this is the basic next bond, right? I need to clarify this before I move on. So if you have 2 bonded away, so this is theta, this is again this theta. Someone can help me, what would be this term if I equals to j minus 2? Well, they're basically next to each other. I heard a little bit of noise here. Anyone? The next to. Yeah, it's very close. So you're going to project it first to the original past, right? So this would be what I have left in terms of L cosine theta, because that's how much has been following the first bond, as we know here, right? And you're gonna also have another projection into the first bond. So you're gonna write as L squared cosine theta squared. Because there's one projecting, you lost a little bit. What left is cosine theta, and you're gonna see how much crosstalk you have first and third. Does it make sense to everyone? You need to multiply by it twice. So in other words, the more, if it's a free joint chain, the more your chain goes along its way, you're gonna have less projection or following what its original bond is. Now we can write it as a generic term. So if I and J are quite far away, so we can write as L1 dot Lj as L squared R I minus J for any two bonds in the system. And this is in the power law, so if I equals I and J are just one bond away, you need to multiply by once. If there's 3 bonds away, you need to multiply by, this is cosine theta 3 times. So you will see why I need to do this, because then we can simplify this very complicated equation in a moment. Okay, so the further the bond away, the further apart I and J, let's say I and J are 100 bonds away, you will see this will be 100 times. And you know alpha is larger than 0, but smaller than 1. It's almost 0. It's very small if you multiply it by 100 times. In other words, in the free joint chain, if you talk, you see how much, the projection they had last bond, 100 bond away to the first bond, it will be minimal, almost nothing. Okay? That's the physical meaning about this. Free rotation chain, a pain, right? We're halfway through our entry, so let's continue. Now we know this equation. You can start to get this better, because if you plug that into that equation, you will be able to solve everything mystery about free rotation chain. And let's do that. So IE squared, again, this term will not change. It's a diagonal term, it's always multiply itself. The angle is always cosine 0 equal to 1. Now this part, for any I not equal to J, Li, right? So we're going to focus on the second part a bit to discuss how we can expand all the non-diagonal term and how we can simplify it into something very easy to understand. Now I'm going to erase a little bit here. Okay, so I'm going to rewrite the term we have. I not equals to J. It's right there. And L-I-L-J. So this is basically the second half of it, and we will try to understand how you can rewrite this. It's not too complicated. So if you do the math, talk about, that's basically what it is. So you can, this is cosine theta, you just need to multiply it and see how far they're away using the equation right there. Any questions so far? If not, let's continue. All right. We're going to play again some of the mathematic tricks to simplify this seems very daunting equation. L squared is basically a number, so we don't need to worry about at this point, right? It's just a L multiplied by L, so you can take this thing out and just worry about what's the value about this term. And if you realize I minus j, take it absolute, it's symmetric. If you remember the diagonal matrix we draw, it's symmetric from top, bottom left to the top right. So you further simplify it by defining a term called k. Because you don't need to worry about diagonal term, and there's only half of it you need to calculate. Right? So if you simplify that, that will be 2 times, we come with the term k. I'll explain what the k is. I'm going to draw you the diagonal imaginary term. So we only need to count everything here, right? And you only need to count it once. So what I did is just replay this one. What we need to count is first one, then second, then 3 of them, then 4 of them, then add everything together. That's why I defined a new term, k equals to 1, can add up all the way to n. So this is 0 to n row. So how does it work out? And because there is a diagonal on the top, they're the same. So this is where this 2 is coming from. Because we're only going to count half of them, then multiply by 2. Right? Everyone is following with me for where this 2 coming from? Great. Yeah. The appetizers for this very big steak is hard to chew, right? I know. Follow me. Hang there. So, why don't we plug in some of the k and try to understand what it is? So, if k equals to 1, that's basically tell you how much term that you have next to each other. Let's put k equals to 1. So you're going to have the term. Right? If you put the k equals to 1 here, that's basically telling you all the terms next to each other, how many of them. So you can see L, I, N, L, J, they're next to each other, going to be this row. Right? Make sense? L, I, and J are just one number apart each other, going to be sitting next to here. Because this is L21, L2, L31, L32. And this will be 4-3, this will be 5-4. So anything that just the one number away will be all concluded here. And you have total number of n minus 1. Right? Because if you count from top to bottom, it's total of n. You take away the first one, you're only left with n minus 1. How about k equals 2? You're going to equals 2. Right? If we put k equals 2 here, that's what you would get. And its physical meaning about this is L squared with alpha 2, n minus 2. So you basically now start count this row, anything like 3, 1, 4, 2, blah, blah, blah. So basically it tells you L4 bond, L2 bond, how much they are away. There are 2 bonds away. That's where this alpha 2 is coming from. And total number of them is n minus 2. If you do this all the way, then you can count everything.
Are you saying your column K is this way, like across the diagonal middle?
Oh, K is not a column, K is
Okay.
just a constant, a new constant we put in. It's not related to I and J at all. So still, this is going to be Lij, right? I is the first term, J is the second term. K is just a new constant we put in. K is not related to I and J.
I thought K was related to the relationship between I and J, so how far J.
Right, right,
Okay.
exactly. So K is it?
K equals the absolute value of J
Okay.
minus I.
Right, right. The furthest distance between J and I, exactly. Okay, so basically this equation is a summary of all the terms of diagonally. We sum everything together into this beautiful equation. Great. 70% all done. We're very close, okay? So, nk, why don't we expand them? So, you can expand this equation to be two parts, right? This will be one part, and this together with k will be second part. Make sense? So let's do that. You're gonna still have the two. You're still gonna k equal to 1 and minus 1. You're gonna pull the n out. That's the first part of it. Very simple. All I did is put the n, pull it out. So this is as simple as a bracketed to b minus c. So all I'm trying to do is get this, ab minus ac. Okay. So this is the first part. Minus, we're now going to move the k to here. K L squared. Okay. Nice and fancy. So now we're going to solve what is this equal to, what is this equal to, then we are done for the free rotations. Simple. I'm going to keep the tops, because at the end of class we will know what it is. So, this is sounds very complicated. So, what part is constant and what is not? Let me rewrite this. So you will have 2, right? K equals to 1, 2, and minus 1 and L squared alpha K. So n L squared is constant. What left is not constant, it's just a K. So this is a math problem. We should have a mathematics professor to teach you this part, right? But unfortunately, I have to teach you. So I did a crash study last night, and I think I understand what it is. I'll explain to you this very complicated crazy equation. How does this equal to? All right. So follow me. So what does this mean? So let's first expand this part. Let's first get to the physical meaning of that. So this equation particularly, let me write here. K equals to 1 to n minus 1 alpha k is equal to a number start from k equal to 1 all the way n minus 1, right? So that means you need to count everything from 1 to the last. This question in the back?
What was K again?
K is just a number. K will equal to 1 to n minus 1, and k is the distance between the bond, two of the bond we are counting. Okay, so k equals to 1, and we're going to add a k equals 2. So this is equal to, if I write this, you will see it's very simple, right? This fancy, complicated equation is basically you want to add all the terms together. And this will be magically become yes. That's basically the top term. These are the same, although it looks very complicated from top to bottom. It sounds like a magic to you, right? But it's very easy to understand. So this is something in mathematics called Taylor expansion. This very famous professor, probably a Taylor, and he made it, and he had a couple of drinks and he published because it's got named after me. And indeed it is named after this particular person. But from a normal person perspective, how would you understand this? It's actually easy to understand if you do it reversibly. So what do I mean is, let me move this thing up, okay? Right, the same equation. This is equal to each other. So if you do a very simple math, I'm sure everyone can do, is move this to here and multiply. So basically it says 1 minus alpha equal to, this is correct, right? So then it makes sense, because I'm going to write the first part is 1 multiplied by everything, so it will basically stay the same, right? So minus alpha multiplied by this, what it will be? Minus alpha squared, right? Minus alpha 3 times, right? Let's keep going. What is it? Now you can understand? You can understand? Because now they basically cancel out each other, equal to alpha minus alpha infinity. If alpha is big enough, it will make sense, right? Because this two cancel out each other, top to bottom. Simple, right? Okay, so good. Everyone is good at Taylor expansion. So, in a nutshell, the first part of the equation will equal to 2nl squared alpha divided by 1 minus alpha. Right? We just talked about this right there. Alpha 1 minus base. And minus this term. I do not want to go through all the mathematics again, but you basically do the same. Now consider what k alpha is again. So this term will become alpha minus 1 alpha squared and 2nl squared. Okay? So similarly, you can do another Taylor computation to simplify the second part of the term to be this. Okay? Good for everyone? Let me make sure. Yeah. Okay, so now, how does everything add together now? We're going to put everything into this very complicated equation and add everything up. The complicated equation is right here, right? So for free rotation chain, we're just going to put everything in and get a final answer. Let's take this slow break. Make sure everyone is catch up in this part.
Why is the denominator in that very last term squared?
If you want, we can go through a little bit in more detail. So let's go through it one more time. I didn't talk about how we actually, because there's one more k term here. If you do Taylor expansion for, let me do it here. If you do the Taylor expansion for this term, this will equal to, and if you look at this part, it's basically a Taylor expansion for k, alpha k. So that's a conclusion. They're slightly different. I'll show you a little bit more if you're interested to understand this particular equation. So that comes down to, I need a little bit of help here. So this comes down to basically equals to alpha 1. Okay? What differs is basically the top term. Okay? But it will not matter in this particular equation because while you do free rotation chain, you will realize this term will go away because there's n term in front of it, which we will talk about in a minute. Alright, everyone is following in this part how we did this very crazy Taylor expansion, get the number. So we are very close to finish the last piece. It's just going to be one more cut for our steak we are done. Good? Alright, let's enjoy the last cut. We start off with this equation. We come to here, expand them into different terms. So I want to come back to here, okay? RE squared equals to NL squared plus the bottom of right there, right? So 2NL squared there's another 2NL squared. There's going to be alpha 1 minus alpha squared. Is everyone following for this part? How we get here? Yep.
Why is the second term added but subtracted right there?
Oh, my bad. It should be subtract. Okay? Good call.
Where did the
I
N come from with the second term
Yeah,
there?
let's talk.
I was about to say that the extra term. Very good call, Molly. So that's actually the why this term actually doesn't matter because when you count the n gonna be close to a very large number, right? A very large number. And this term will be always much larger than the last term. Because they are not the same on the same level. Alright, it's an indication I need to wrap it up. So let's do this. So if we eliminate this term because it's not going to be relevant for this calculation, if you just think about n, if n is 100 times bigger, if you eliminate the last part, it will be only within 1% error. In reality, as you know, for polymer, n is like 10,000 or even bigger, so it's totally fine. You throw the last one away. Make sense? So, all right. Now the math becomes simple again. NL squared is always the same, right? You also have this part, so it's equals to such a beautiful mathematics. I know I hate to see this long equation. This is better. isn't it? So let's combine these all together. N L squared. So this will be equals to 1 minus N. That's where the free rotation chain tells you what the end-to-end distance is. And alpha is basically equals to cosine theta. So in other words, you can change this to cosine theta. Right? The next class start at 3. But
Yeah, no, they'll figure it out.
yeah. So that's a beautiful end of free rotation chain. Shows you what is the value of end-to-end distance. And anyone can remind me what is free joint chain for end-to-end distance again? And what's the difference is basically the second term, right? That's coming from the fixing angle is affecting it. And how much of real physical effect it had on the polymer chain? As you know, this term it will be between 0 and 1, and so the bottom part will be, this will be again between 0 and 1, this will be a little bit larger than 1, so in the end, this will be larger than NL squared.
The actual end-to-end distance would be the square root of that whole.
Right, right.
Okay.
Yeah,
So
exactly.
REE is that.
Root of that.
Okay.
Yes. So we are writing as IE squared, just for
For
simplicity.
simplicity.
You know, I don't need to write this root square all the time. But you got the idea. The physical meaning is when we consider the angle of the bond when it's fixed at a certain angle. What translates in real meaning is your polymer will be more rigid. So the same amount degree of polymerization and will translate to be a bigger polymer chain in the physical world. And how big this is, people actually, I think physicists are lazy, so they define a term, which we'll cover in that next class. This is called characteristic ratio, which we will talk a little bit more in the next class. So let's wrap it up. The entry is finished. We didn't have time to go into the dessert, so we'll do it next time. So let's recap for this class. What we did in this class is we had a little bit more in depth compared to the first class. We talked just at the very beginning how free joint chain works. This class we dived into the math, understanding what is free joint chain, and we also played and everyone survived through the complicated math to understand free rotation chain is in the end. The physical meaning of what a free rotation chain is. So for the next class, we're going to go into the next chapter, talks about inter-rotation chain and relate to the mathematics. Please take a look at the chapter 6.3 in your textbook. Okay, so that will be it. Is it still going? Good. Oh.
Last semester.
Huh?
No.
So that's where all these terms come from. Cool. Exactly. That was my life.
Alright, I'm gonna go to a phone call. 5:30 is.
Right. One more short notice for the class, it should be in the YouTube, so I'll send a link to everyone. If any part of the explanation was not clear.
You think 5:30?
Yeah.
I think that's what he said last time. There's no talk about
You know,
makeup lecture or just?
no, that's the help session from Corner. Is he doing a makeup lecture?
Yeah, I'm pretty sure he is.
That's a great question.
Just need to know if I said anything to the coach or,
Yeah, I need to go work out before he gets mad that I abandoned him for 12 hours.